We have gotten quite good at, as a community, at predicting the properties of materials through what's called first principles computation, which is using the laws of physics to predict materials properties. And so as we're getting better at that, more and more the limiting factor comes that, we create all these virtual materials in the computer that are really interesting and that would have great energy applications, but the question is, how do we make them? We're trying to figure out if computers can help us guide how we make materials, because today, if we want to make a totally new compound, we basically send somebody in the lab and hope for the best. And sometimes we're lucky and in a week the material's there, sometimes we're not, and 10 months later we still don't have anything. And that's because we don't really have any guidelines of what can be made, how can it be made. So with this project we're sort of trying to solve that problem. Here we're using a very different approach than we're normally doing in science. Normally in science we're trying to come up with the principles and derive the laws and then sort of try to implement them. Here we thought we'd do a very different approach, is to ask the question, people have done so much synthesis of materials, so can a machine learn that by absorbing that knowledge? So we're trying to use machine learning to actually learn the rules of synthesis. And the way we do that, the first thing to do is that the machine has to be able to absorb all this information. So this project has set up all the tools to essentially machine read papers. So we have something like 3 million scientific papers that we got through collaborations with publishers, and we've actually trained the machine to extract and learn synthesis recipes of that. For example, we have several really cool materials in the design pipeline. We have one, say, for sodium batteries, which would, make quite inexpensive batteries that could be used in the grid. But an example that's really cool, everybody wants to make solid-state batteries today, because solid-state batteries with lithium-ion would be very safe. They wouldn't burn anymore. They would be much more stable in the long term. And so for that, you need to make what's called a solid-state electrolyte. It's a material that makes ions flow in and out of it very fast. So computationally, a team that included myself and working with a company came up with a material that would have the fastest transport of lithium ever seen in the world. Well, this material has not been made yet. So this is one example. If we actually could figure out in the lab how to make it, we would have a really novel material for lithium batteries, could put that in lithium batteries and could make much safer batteries, right? Could actually go and make it in the lab. If you had cheap and reliable energy storage, you could transform the world, right? You could transform the way we make and store and distribute energy. Solar and wind, for example, are already quite inexpensive. They're widely deployed. The only piece you're missing is storage. If we actually had cheap and long-lived energy storage today, we could transform energy production completely, right? This is really the limiting factor, which is why it's so important. And that would allow us to completely clean up electricity production. If we had even slightly cheaper energy storage than today, we could revolutionize transportation, right? We're already close, right? You already see electric vehicles, they're already pretty good. But imagine now that you can cut the price of them in half and you can extend the range by a factor of 2, then everybody would buy these cars because they're sort of a better driving experience already. You just need cheaper energy storage. So it really is such an important problem for society today. A lot of the ideas we work on are very generally applicable, so they could see implementation in things like smartphones. That's probably, for example, where we see solid-state batteries go first, because it would be very safe, right? And there's been all these safety incidents with smartphones, with laptops, and that's because they tried to pack so much energy in a small space. But they would definitely make their way ultimately into things like vehicles. That's the fascinating thing about today's energy storage technology, that you see these technologies that both work at the small scale and then also work at the larger scale. So it really has potential for very broad impact. I think what we're finding is that to teach a machine to read and understand papers is actually complicated, because humans write in complicated ways, we find. Very non-systematic. Sometimes information is missing, and I think as humans we have the ability to fill that in often, but a machine doesn't. So I think what we're actually seeing is almost imperfections in human writing more than in the machine interpretation, and those we cannot fix. But I've learned a lot about writing and syntax and the all complicated ways people spell out things in papers. And maybe this should tell us something about how we should report science in the future. It's like we seem to do very rigorous science, then we write it up in a sort of like convoluted way, and now we're having a machine trying to extract it rigorously again. Maybe we should skip the middle step. The other thing I would say, when you write your paper, think that a machine might be reading it, not a human. So be clear, machines are not very smart. So one of the things we do is work with like trying to design battery compounds with metals or elements that are not so scarce, that don't have such a high mining impact. So there's a big story these days around cobalt, right? Cobalt is rare, is mainly mined in Congo under unethical conditions. So in other projects, we're trying to design materials that are cobalt-free. So in general, the fact that if you can computationally design things, you can have a much broader reach, right? You can look at many different compositions. And if now we can add to that the synthesizability aspect, we can be much more effective, right? We don't design in a vacuum anymore. We only design what we will know how to make.